In this activity, we're going to use the ideas of state space tracking that we developed in the last couple of videos. Here you're going to be looking at just the simple spring mass damper again from the state space perspective, which I've already kind of given you the equations for. We're going to be considering a feedback control law that uses two gains, a proportional and a derivative gain inside this overall gain matrix, multiplying the state, and then this KR term, which is the gain that we just talked about in terms of tracking. So in general, you would design KP and KD in order to guarantee that you achieve stability, and then you design this KR term according to what we just discussed in terms of tracking. So in this case, what we're interested in doing is being able to show how we would calculate this value of the control gain KR based on trying to achieve a static reference. That would be some R0 value in steady state. And then once you do that, I'd like you to look at what the value of U is, the input, when you're in this steady state condition, and kind of interpret, it has a nice physical interpretation, what that control value means at that point. So go ahead and take some time and look at this problem, and then we'll go through the solution. Okay, so we'd like to take a look and calculate that this gain KR such that we guarantee a desired reference. And so one of the things that you could do is you could compute this KR from the slides. We had this relationship that KR would be -1 over C times A plus BK inverse times B. And so you could calculate it this way and you'd get the right answer. What I'd like to show you is just, again, the intuition behind this. So we're going to actually solve the set of equations directly. But again, you could calculate the same gain value in this manner. So this is our differential equation, our essentially system of differential equations. And remember, in this context, x1 is the position and x2 is the velocity of the block. And so what we're interested in doing is guaranteeing that essentially, in this case, the output is simply just the first element. So that would just be x1. We want x1 to achieve some sort of reference. And in this case, the reference is going to be this step input, which is essentially just a constant value that we set. And so what that means is that in steady state, we would like our system to look like, we would like x to be essentially r and 0. So we'd like it to stop moving. So that's why this is 0. The x2 component is 0. And we'd like the position to be the desired value, our reference. Or if we wanted to use the terminology of the prompt, it would be R0. So one thing we can do, just like we did in the previous slides, is we can set our differential equation equal to 0 because we're setting the time change of everything to be 0. So here we're setting x, but here we want this x dot to be 0. And so if we do that, we're just going to write out the two system of equations that we get. So in this case, remember this x is x1, x2. And so if we multiply this out, the first line just gets x2 multiplied by 1 plus 0. And so that means that essentially x1 dot is equal to x2, and we want to set that equal to 0. What's x2 dot equal to, which we're going to again set to be 0. This is a little bit more complicated here, but now we have this x1 term multiplied by kp minus c, and x2 term multiplied by kd minus b, and we have this r term multiplied by kr. And so all of that gets put down into this equation. And notice that we have these 1 over m's. Since we're setting all of this equal to 0, we can go ahead and just multiply both sides by m to get rid of those. All right, so now we have this equation, and we'll go ahead and make the substitution that x2 is equal to 0 if the first equation is satisfied. So by plugging that in here, we get rid of this term, which leads just this. And so far what we've done is we've just said that in steady state, we want the system to essentially stop moving. Now what we're going to do is we're going to actually say we want this value x1 to be equal to our desired reference. So now we're going to say that y is equal to x1, and we want that output to be equal to our reference r. And so if we make this substitution in for x1 here, or just plug r straight in there, and we get this expression. Notice r appears in both terms and the zeros on the other side, so we can get rid of that since it's just this constant value, which leaves us with the expression that kr, our gain that we want for our reference, to track the reference, is just c, which is the spring constant, minus kp, which is our controller that is proportional, that's the gain with respect to x1, or the position. All right, so notice that if we do set the reference to be 0, then one of the consequences of that is that in this equation, x2 would be 0 and r would be 0, and so then you're just left with this expression, which then would just drive x1 to 0. So that's kind of consistent with what we wanted, no matter what the reference would be. In that case, you'd be stabilizing x, but in this case, we're interested in making x track a constant reference. And so now we get down to the interpretation of this. And so if we look at the value of u, so now we're going to calculate what u is. We're going to calculate it at steady state. So once you actually are tracking the reference, so that means that y is equal to r, and the block stops moving. Essentially, the x2 velocity component can be ignored. So if we go ahead and plug in what this value is, it's just kp times x1. So that's x1. Because x1 and y are equal to r, we can just plug in r there. X2 is going to be 0 because we're in steady state and that velocity is stopped. And then we have this term, which is kr multiplied by r, which is the rest of this expression for the input. And so what you notice is the fact that the input at that point in time, essentially what this is doing is it's the proportionality piece that's stabilizing it. So it's the stabilizing part here, namely the x1 and the kp term, give us a force that we would be exerting. So remember, this u is this external force that's pulling the block to the right of kp times r. And what the tracking part does is that it generates, notice this piece, this kp times r, this generates something that essentially cancels out that term. And then what it does is it adds another term that is c times r. And c times r actually represents, so when this block is at r, so once we've stretched this block so that it's centered at r, then the stretch of the spring is such that the force generated by the spring is the displacement, so that would be r, multiplied by the spring constant, which would be c. And what we're saying is, at this steady state, when the block is at the reference, the input u is actually equal to c times r. And so that means that what we're doing is we are generating this static input, essentially the input that happens even when x goes to 0, such that we are counteracting the spring force that's pulling the block backwards. We're adding a force that is exactly equal and opposite of that. So you have CR pulling the block back, which is the spring, and you have CR that is given by our controller U, this term, this kind of extra static term. And so what it represents is kind of this, what we'll call preloading of the spring to shift the block over to the right. Essentially, so that creates a new neutral position by adding this extra kr times r term. And so that's kind of the physical interpretation that helps understand how this controller is split into a stabilizing piece and into a piece that achieves the tracking.